Good morning. Welcome to the second day of the M-Theory and Mathematics Conference. The first speaker is Chris Hall, who's going to tell us about dualities, K3, exotic branes, and Orientifolds.
Okay, thank you very much. So I'm going to be talking about some work with my student Nipul Chamjamras, described in these three papers. But before I start, I thought it might be I thought it might be useful in this present conference to make a few comments about M-theory. 11-dimensional supergravity and branes play a very important part in this, but it's very important to remember that that is not what M-theory is. It's not just a theory of branes and supergravity. A key feature is that it needs to be a quantum theory, and if we compactify on S1 or K3 or Calabi-Yau, we should recover a perturbative string theory, which in particular has an infinite spectrum and has a lot of features associated with conformal field theory. For example, there are solutions of string theory which are understood formally as conformal field theories. For example, from tensoring together minimal models or from some elaborate construction involving, say, parafermions. And some of these may look very different from any kind of space-time picture. So that already in string theory we have some richness, which is something which we're a long way from understanding how that could arise within M-theory. In particular, the perturbative string theory doesn't lift to a membrane perturbation theory in 11 dimensions, even though the string solution lifts to a membrane solution. And there's a lot of other features of string theory and hence of M-theory. For example, a lot of the solutions are not, there are many solutions which are not conventional manifolds, which are the arena of supergravity. There are singular spaces which play an important role in the theory. There are non-geometric spaces. I'll say some more about this, but one example of these would be, for example, some of the abstract conformal field theories which give non-geometric solutions of the theory which can't be understood in terms of supergravity. And there's, in some contexts on toroidal spaces, for example, the double geometry seems to be the arena in which string theory lives. So we don't know what the fundamental ingredients are for M-theory or even what the degrees of freedom are. And another feature which any theory of M-theory has to build in and explain is its relation to field theories, to matrix models, to holography, and also has to give an understanding of what happens in the still mysterious M5 brane theory. So I think despite around 25 years of work on M-theory, there's in some ways we've only explored a few of the areas near some of these cusps in this diagram, and there's a lot to understand about what happens yet to understand about what happens in the middle. So my story today, I'm going to be talking about some of the aspects which follow from the duality between 2A strings on K3 and heterotic string or type 1 strings compactified on T4. And as we'll see, exploring this duality, this old duality, and some of the dualities which follow from taking duals of this, will lead us to some new understanding. So if we start off with the type 1 on compactified on a 4 torus, if we t-dualize that on n circles, one ends up with a set of d branes with 9 minus n and d9 minus n branes and corresponding Orientifold planes. In this theory, at strong coupling, one finds that there are new kinds of planes which arise, so-called O-star planes, which turn out to play an important role in, for example, understanding some of the symmetry enhancements which occurs in these theory. and which are not understood, which don't arise in the weak coupling and are not part of the conventional story of the Orientifold planes. And because these arise at strong coupling, these kinds of objects are important to understanding the kinds of strong coupling limits of string theory which arise, for example, in M theory. And as we'll see, there's a chain of dualities which starts from type 1 on a torus and relates this to the heterotics and take this to 2a on K3. It takes D branes to Kaluza-Klein monopoles, which will then, which are smooth geometries given by the Taub-Nut geometry or multi-Taub-Nut geometry, and so provides, in some sense, a geometric realization of the D branes. And one of the questions I want to explore is what happens to the Orientifold planes. Can we understand the Orientifold plane? Do the Orientifold planes also lead to a geometric dual? So it's a similar question to one which was asked by Ashok Sen some time ago, where he looked at Orientifold 6 planes and lifted them up to M theory and related these to an Atiyah-Hitchin metric. But this story will lead to, in this particular set of dualities, will lead to a new kind of geometric dual for different kinds of Orientifold planes. And putting these things together with these Kaluza-Klein monopoles and these duals of these Orientifold planes will give a new picture of K3, and in particular one in which one can understand some of the dualities acting on this and its relations to, for example, D branes and so on, rather explicitly, and at the same time gives a new understanding of some of the strong coupling physics, for example, the O star planes, and how these arise in the theory. So part of this, a related part of the story is that if one starts off with conventional branes and does enough dualities, it relates them to not the conventional branes which are the familiar ones in M3 talks, but some which are referred to as exotic branes, one with low codimension. So for the ones with codimension 2, for example, 7 branes in 10 dimensions or 0 branes in 3 dimensions, these give rise to, the branes which arise in this way are ones which have got a monodromy around the centers, which are points in this plane of this transverse plane with 2-dimensional surface, and they have U-duality monodromies around these, and so are ones which have got U-duality transition functions in a sense, and so are not conventional manifolds but are U-folds, and these are explored by De Boer and Shigemori. The story I'm going to be talking about today involves codimension 1 exotic branes, which are duals of, which are domain wall-like objects rather than 7-brane-like objects, and these arise as non-geometric duals of D8 branes. And this story says that if we sort of start T-dualizing type 1, if we T-dualize on one circle, we get what's known as type 1 prime theory. The circle is T-dual, the T-dual of this circle becomes S1 mod Z2 with 2 fixed points, and so can be thought of as, and so if you take the circle and identify it under the Z2, it takes the 2 hemicircles and puts them on top of each other, and you end up with something which could be realized as an interval. And this could be, and so we could get a theory with this theory on living on an interval across nine-dimensional Minkowski space, and there are 16 D8 branes moving around on this interval, and there are Orientifold planes at the ends. However, in all of this story, an isolated brane is not a consistent configuration. For example, a single D8 brane, or more generally, these exotic branes are not consistent configurations on their own. One of the story is, part of the story I want to discuss is how to embed these in consistent solutions of string theory. For the D8 branes, this is done by embedding them in type 1 prime theory. And we'll see that looking at the corresponding story for these other branes, we'll embed them in stories which arise from the duals of this type 1 prime configuration. And as we'll see, this will in turn lead us to the K3 story that I talked about on the last slide. So an important part of this story is understanding the relationship between symmetry and geometry. Space-time you can think of as constructed from local patches, and all symmetries of the physics can in principle be used in the patching. If it's a symmetry of the physics, then the physics won't see the join between the patches. So if we use diffeomorphisms as transition functions, you construct a manifold. If you use gauge transformations, you construct a gauge bundle over that manifold, and so on. But in string theory, there are new kinds of symmetries. There are S, T, and U dualities. There's mirror symmetry. And if you use these in transition functions, then you can construct new kinds of objects which are often referred to as non-geometric. It's a bad physicist name. And if you have T-duality transition functions, you get T-folds. U-duality ones, you get U-folds, and so on. So T-duality takes a circle of radius r to one of radius 1 over r. And so if you have a caricature of a T-fold patching, you could be thinking of gluing a large cylinder to a small cylinder. In general relativity or supergravity, this would not give you a smooth configuration. The metric would jump. But in string theory, you can glue momentum modes here to winding modes here and vice versa. And because string theory on a circle of radius r is equivalent to string theory on a circle of radius 1 over r, the conformal field theories are the same. You can join these together and get a non-geometric space. And so if you try and think about what this might look like, you could start with a small circle, slowly come around to get bigger, and then glue those together in that way. So to look at a more precise example of this, I want to think about a background which is given by a 2-torus bundle over a circle. And compactifying on this sort of space will give rise to some interesting examples. So normally, if you're constructing a smooth manifold, you'd allow the transition function, the monodromy, to go around here to be a large diffeomorphism of the 2-torus. And in that way, we construct a smooth manifold. But I want to extend that to allow this to include the T-duality group acting on this torus, which is O22Z, which includes a subgroup. There's some extra Z2 factors, which is SL2Z cross SL2Z. One of them acting in the familiar way on the complex structure modulus of the 2 torus, and the other acting on the modulus, which is given by the value of the B field, which is a 2 form, so it's proportional to the area form on this 2 torus. And I times the area of the 2 torus, the value of the area. So these two moduli characterize the geometry here. And a simple case is where we have the flat metric on T2 cross S1 and have a B field which depends linearly on the coordinate x of this circle and is proportional to the volume form dy cross dz, wedge dz on the 2 torus. And as you go around this circle, x goes from 0 to 1, and so B shifts by m times the area. And so this means that there's a shift of the rho modulus by rho going to rho plus abnormalized things, so it just turns out to be shifting by this integer m. if we take one T-duality with respect to one of the circles here, it turns off the B field and one ends up with a 2 torus bundle over the circle, which can also be thought of as a circle bundle over the T2. And this is, so here we see that we have the cross term in this metric would represent the connection form on this bundle. And as we go around the X circle, the complex structure modulus undergoes a shift. And this space is a well-known three-manifold known as the nilfold. And this will play a role in the later story. And if one does another T-duality, what happens is that each time one does a T-duality, it acts on the monodromy by a conjugation within the T-duality group, and it changes the monodromy to a new O22Z transformation. And now, if one does a third T-duality with respect to the other circle in the fiber, then one ends up with something which looks like a reasonable metric and B field until one remembers that X is meant to be a periodic coordinate, so that, and this is clearly not a periodic function. But what happens as you go from X to X plus 1, one can check that the modulus rho undergoes an O22Z transformation, which is given by this fractional linear transformation. And so this is an example where there's a T-duality monodromy as you take this 2 torus around here, and this is give an example of a T-fold. So this gives a nice set of examples which have often talked about, but none of these on their own is a solution of string theory. So if one goes back here, then a 3 torus with flux, without the flux, certainly gives a solution of the Einstein equations, but it's turning on the flux will then mean that this will give you a non-trivial stress energy tensor, but a flat, but a zero curvature, and so the Einstein equations won't be satisfied. So one of the issues is whether you can embed such things in string theory, and it turns out that one can find bundle or generalized bundle solutions in which these 3 spaces that I talked about on the last slide all appear as fibers in this space, and the dualities I talked about on the last slide then act fiberwise. And the simplest case is where I take these three-dimensional spaces and fiber them over a line. And if we go back, then the simplest thing to start thinking about is this nilfold, this three-dimensional smooth manifold, and fibering this over a line, which in particular implies that we'd allow the moduli of this space to depend on the coordinates of the line. And it turns out that when one does this, one can do this in such a way that you end up with the 4-dimensional space being hyperkähler, and hence Ricci flat, and hence a solution of the Einstein equations. And the way one does this is by playing with the famous Gibbons-Hawking metric. It's a well-known solution that gives a hyperkähler metric, a non-compact hyperkähler space with S1 symmetry. I'm sure you'll be familiar with the metric. Here we have an R3 with coordinates tau, x, and z, and we have V, a harmonic function on this R3, and this omega is a 1 form which satisfies this equation. And V as a harmonic function can have delta function sources at a set of points with M an integer. And so this constructs an S1 bundle over R3 with these points removed. And in fact, this space can be extended to these points in a way which is regular at the sources if M equals 1. And in this case, one constructs what's known as the multi-tailed nut solution. And there are simple orbifold singularities if M is bigger than 1. So here we have a harmonic function on R3, but we can also consider smeared solutions in which we take V independent of 1 or more coordinates. And one reason why we might want to do that is if we do that, then we can take the coordinates which V is independent of as periodic, and then one can compactify. So if one does this, one ends up with a way of compactifying these solutions, but at the expense of getting a metric which is typically singular. And one of the stories I'm going to be exploring is how to deal with those singularities. So if we take this solution and smear over x and z, it says y here, but it should say z, then we end up with a function depending on just one coordinate, tau. So a harmonic function on one coordinate is linear. We can generalize this to have things which are, say, piecewise linear, which are continuous, but where the gradient has, jumps at, say, tau equals 0. And then we would have a singularity at the kink here, where you have this jump. In this case, you'd think this is interpreted as giving a domain wall. There'd be a two-plane dividing the space into two parts, and the jump in the gradient is associated with the energy density of a domain wall. And this picture is justified, as we'll see, because as we'll see, this is dualized to other domain wall solutions like the D8 brane, where this is seen to be the right interpretation. So if we take the smeared Gibbons-Hawking metric with V linear, and then we can take x, y, x, z, one of these, x, z, and y to be periodic, and then for fixed t, for fixed tau, this becomes just precisely the nilfold metric if we set v equals 1. Or a rescaling of that if v is not 1. And this is an S1 bundle over T2 with fundamental characterized by the 2 form, which has got characterized by this integer m, which is known as the degree of this bundle. And if we take, this can be thought of as a quotient of a group manifold. The group manifold is the group manifold of the three-dimensional, of the Heisenberg group, which is a three-dimensional group. And taking a discrete quotient of this by a discrete subgroup. And this gives rise to a four-dimensional space, which is the nilfold fibered over a line. And we can introduce domain walls by allowing jumps in the gradient, giving jumps in the degree. And we can get a string solution by taking this four-dimensional hyperkähler space and taking a product with six-dimensional Minkowski space. And then for a single Taub nut, this gives a Kaluza-Klein monopole solution. And in the smeared case, it's giving a kind of smeared Kaluza-Klein monopole wrapped on a 3 torus. So now we can look at the T-dualities. If we look at the nilfold fibered over a line, if we T-dualize that, we end up with a 3 torus fibered over a line. So if we're doing the first T-duality I had on the slide a few slides ago, we get a 3 torus fibered over a line, and the four-dimensional space is conformally flat, but with a B field turned on, whose field strength is the dual of dV. So if V just depends on tau, then this is a 3 form in the x, y, z directions, and we have that, and there's a dilaton turned on, and V is linear or piecewise linear. And putting this together gives a 10-dimensional solution, which is the familiar Nerva-Schwarz 5 brane, but where the transverse space is now R cross T3, and the 5 brane has been smeared over the T3 coordinates x, y, and z, so that these are identified to give the transverse space R cross T3. And then we can do another T-duality and get the T-fold fibered over a line, and you get some messy equations like that. And this is a string, and this can give a string solution by taking a product with six-dimensional Minkowski space. And this can be thought of as a smeared version of one of the exotic branes I mentioned earlier, which is given this name or this name in the literature. So all of these can be generalized to multi-domain wall solutions where one has the function being piecewise linear with a set of jumps in the gradient at points tau 1, tau 2, and so on. And the charge at the domain wall tau r is an integer given by the jump. And we have this metric. And we can also consider what's sometimes called a single-sided domain wall. So if we had V, which was given by this for all values of tau, this is symmetric under taking tau to minus tau. And so we can take a quotient of this solution by this reflection, and the result can be thought of as a single-sided domain wall at tau equals 0. So these are still not consistent string backgrounds. Away from the walls, we get a hyperkähler space, and the duals give conformal field theories, but the domain walls are singular. And the dilaton and the function v will typically blow up unless we end the interval with, say, some single-sided domain walls. And with these single-sided domain walls, we need some negative brane charge to cancel the positive brane charge of these domain walls to get net charge 0, which we'd need in this situation. So to understand how to deal with this, we're going to understand this by relating this by a change of dualities to situations which we understand. So if we started off with a Kaluza-Klein monopole, this T-dual to a Nova-Schwarz 5 brane, and this is S-dual to a D5 brane, and then 3 more T-dualities will take you to a D8 brane. If this Kaluza-Klein monopole was smeared over 3 directions in the way I described it a few slides ago, then this is also smeared on T3, and this D8 brane you end up with is wrapped on T3. So this was a nilfold fibered over a line. This was a 3 torus with a flux fibered over a line. And here we end up with the D8 brane, which is a domain wall in 9+1 dimensions. And so, as advertised, these kinds of domain walls are dual to the D8 brane domain wall. And to embed the D8 brane in a string background, one needs the Orientifold planes arising in the way I described in the type 1 prime theory, where one has 16 D8 branes and 2 Orientifold planes, one at each end of the interval. And here we understand the singularities which occur at the walls in the D8 brane case. These reflect the presence of physical objects, the D8 branes. And given this consistent string configuration occurring in the type 1 prime theory, if we dualize this, we should get consistent backgrounds for the nilfold and the other dual solutions, the T-fold and the T3 with H-flux. And in particular, we should learn how the singularities I've just described are resolved in each of these duals, and how string theory deals with that. So let me say a little bit more about the type 1 prime string theory. It lives you start off with type 1 on a circle, one T-dualizes and one gets S1 mod Z2 cross 9-dimensional Minkowski space, and as I mentioned, S1 mod Z2 we can realize as the interval, and there are 16 D8 branes of charge 1, which could be grouped together, so you have a set Ni at points tau I along the interval, so that the total number is 16. And these represent the jumps which occur here. And we have single-sided domain walls at the ends, which are realized as these Orientifold planes of charge -8. And I'll take the end points to be tau equals 0 and pi. And then we can have some of the branes sitting on top of these Orientifold planes, giving rise to a charge -8 plus a number of Orientifold planes, number of D branes on top of each of those two Orientifold planes. And so the number of total number of D branes in the interval is given by the sum of the charges at the ends, where the ends are now D8 branes and Orientifold planes on top of each other. And then we get a set of charges like this. So now if we start looking at the duals, we can start by thinking about the supergravity solutions and looking for the dual supergravity solutions. So we can dualize we know the rules for dualizing these supergravity solutions, and we get smeared Gibbons-Hawking and Nerva-Schwarz 5-brane solutions. And there'll be 16 sources which were D8 brane sources and now will become Kaluza-Klein monopole or Nerva-Schwarz 5-brane sources, all smeared over the T3. And then these now will be singular, and so the question about how these are resolved. And at the ends of the interval, we will find the duals of the O8 planes, which we need to understand. So we have this chain of dualities where we start off with the D8 brane, T dualized on 3 circles to the D5 brane, S dualized to the Nerva-Schwarz 5 brane, T dualized to the Kaluza-Klein monopole. Then a further T duality takes you to the exotic brane. And so there's a question about, so for the O8 plane, we go down to an O5 plane. There's an analog, a Nerva-Schwarz analog of the Orientifold plane, which is called the ON plane in the literature. And there's a question about what happens for the Orientifold versions of these, which I'll come to. So to understand these issues motivated by the supergravity solutions, we need to look at the full string theory to understand these dualities. So we start off with type 1 string on S1. It's dual to the type 1 primed on the interval across 9-dimensional Minkowski space. Now if we compactify this on a 3 torus, we get the type 1 string on T4 cross R15. And the same set of dualities which we considered here, we'll take the type 1 primed on T4 to, first of all, to the type 1 primed, T dualizing on 1 circle, which could be thought of as the type 2a string modded out by a reflection in the 9th coordinate on the 9th circle, and an Orientifold thing, taking an Orientifold of that, identifying under worldsheet parity, taking the worldsheet spatial coordinate to the reflection in the worldsheet spatial coordinate. If we do 3 more T dualities, we get another Orientifold of 2b on R4 on T4 mod Z2. S dualizing changes this worldsheet reflection to acting by -1 to the left-handed fermion number on the worldsheet. And then a further T duality takes this to 2a modded out by a reflection in the 4 circles of the torus, that Z2. And this last case gives 2a on an orbifold of orbifold T4 mod Z2, which is a particular orbifold limit of K3. So here we see this chain of dualities giving K3, albeit at one point in the moduli space. And so here we get an explicit understanding of the duality between the type 1 on T4 and the 2a on K3, or at least at one point in the moduli space, from this chain of dualities. So we've seen that the branes, the D8 branes, have gone to gravitational solitons, these Kaluza-Klein monopoles, smooth solutions of the smooth solutions. Is this on? Okay. smooth solutions of the Einstein equations. And so there's a question about what happens the corresponding Orientifold planes. So each T-duality doubles the number of Orientifold planes because it doubles the number of fixed points. Here we get 16 Orientifold O5 planes, and here 16 ON planes. So dualizing the supergravity solution with D8 branes takes us to one with Kaluza-Klein monopoles. And at the same time, and this gives, so we end up at the same time we're getting a space which is a nilfold fibered over a line with smeared Kaluza-Klein monopoles, and the ends of the line giving a geometric dual of these Orientifold planes. So from dualizing, this arises from dualizing the type 1 primed string. So the same dualities take type 1 primed on T3 to the 2A on K3. So this, gives us, shows that this predicts that there should be a region of the K3 moduli space in which the K3 looks like the stuff we've got from dualizing these branes. In other words, in terms, it should look like a set of Kaluza-Klein monopoles arranged over a line, and in between the Kaluza-Klein monopoles we should get a nilfold fibered over a line. And it should also give, and also the K3 geometry should tell us the answer to the question about what happens to what are the geometric duals of the O8 planes. And it's this story which I want to now understand. So this is a safe prediction to make from the string theory, because it turns out that precisely this kind of limit of K3 was discussed, it was understood a year ago by some mathematicians, Heinsohn, Biaklowski, and Zhang. They constructed a family of K3 metrics depending on some parameter t, such that as you take the limit to t equals 0, the K3 collapses to a line interval. And so this limit taking t to 0 is the one which is taking us to the boundary of this K3 moduli space, or a particular component of the boundary of the K3 moduli space, in which there's, for small t, there's a long neck region, which is, so you have a long, thin neck, and each segment of the neck is a nilfold fibered over a line, the solution we talked about before. So the nilfold, as I mentioned, is a circle bundle over a 2 torus with Chern number or degree m. And in different segments, there are different values of this m. And the jump at each point where there's between the different segments, there's a jump in this degree. And this is smoothed out by the insertion of a gravitational instanton, a Kaluza-Klein monopole. And it's that way we get a smooth space, which is given by joining together these nilfold fibered over a line. And the ends of the neck are capped by spaces, which I'll be saying a bit more about in the following slides, which are known as Tian-Yau spaces. So these are 4-dimensional, complete, non-compact hyperkähler manifolds. So in particular, they're Kähler-Ricci flat, which they're non-compact, so they have an asymptotic, and the asymptotic region is asymptotic to precisely the nilfold fibered over a line. So it's precisely the kind of geometry which you'd need to glue onto these neck regions. So from their paper, they had this diagram about what it looks like, what the geometry looks like. So you have this geometry at the end, which is these smooth caps given by these Tian-Yau spaces, which have complicated topology. And in the middle, one has a set of Kaluza-Klein monopoles here. So here, there's the neck is one where all the Kaluza-Klein monopoles are all close to each other in some one region, which becomes fat. More generally, you'd have long, thin neck regions, and then the joins would be fatter regions, which involved a Kaluza-Klein monopole. So to understand this geometry a bit more, we can think about a first approximation to this K3 in terms of the solutions we looked at so far, where we have this Gibbons-Hawking metric smeared over 3 directions. At each point tau, we get a fixed tau, we get a nilfold of degree m. So here, this m of tau is just a piecewise constant piece given by the gradient of this piecewise linear potential. And their construction resolves the singularities. There are singularities at these where these domain walls are at these points T1, tau1, tau2, and so on. And at the endpoints, these are resolved by a Naguri-Waffe construction. And the ends of this interval are resolved with these Tian, where we have these single-sided domain walls, are resolved with these Tian-Yau spaces. So I'll now say a bit more about each of those. So we're looking at a Gibbons-Hawking metric where the R3 is replaced by R cross T2, and the first approximation of this was smearing over the T2. But a better way of looking at this is to take, on R3, to take a periodic array of sources in 2 of the directions, the 2 we're going to smear in. And then we can find a harmonic function by summing over the potentials with sources at each of these points in this periodic array. This gives a divergent sum, but Oguri and Waffe showed how to regularize this to give a harmonic function, which we can now then periodically identify in the x and z directions to get a single source on R cross T2. And near the source, these are non-singular, and near the source you can't tell the difference between T2 and R2, and this looks like, and near the source it looks like a Taub-Nut space. And we can take superpositions to get multiple sources on R cross T2. And one of the price one has to pay in this construction, coming from the way this sum is regularized, is the resulting solution is only regular on a finite interval in R rather than over the whole of R. So we can only use this construction on finite intervals, and these will be the finite intervals corresponding to the segments we're joining together in this long neck region. So we resolve this, so at each of these singularities where we have this jump, we can resolve by an Oguri-Waffe metric with V harmonic on R cross T2 and a monopole charge given by this jump. And near the sources it looks like a Taub-Nut space. And for n sources we can construct a regular hyperkähler metric on some interval on the line. And far enough away from where you have the jump, you get something which looks like the Gibbons, which tends towards the Gibbons-Hawking metric we talked about earlier. So that's fine for the middle, and now we come to the Tian-Yau spaces at the endpoints. So these are complete, non-singular, non-compact hyperkähler spaces with SE2 holonomy, 4-dimensional spaces. Just like Calabi-Yau spaces, they're not constructed explicitly, but there's indirect existence proofs for these. In each case, they're asymptotic to a nilfold bundle, a nilfold fibered over a line. And they're constructed from spaces which are known as Del-Pezzo surfaces, which are complex algebraic surfaces of dimension of give 4-dimensional Kähler manifolds with positive first Chern class. Hence positive Ricci curvature, and they're classified by their degree, which corresponds to the degree of the and this degree of these Del-Pezzo surfaces is given by an integer from 1 to 9. So for the degree 9, it's just CP2, and for degree B, it can be structured by blowing up 9 minus B points in CP2. you take out a point of CP2 and you replace it by a certain, glue in a certain manifold. And of degree 8, except that at degree 8, there's one extra one, which is CP1 cross CP1. And from these Del Pezzo surfaces, you subtract out a two-dimension, essentially a two torus is subtracted from these, is cut out from these, and this leaves a non-compact space, which it turns out admits a metric of this kind. And the Tian-Yau space that you get from this construction is asymptotically to a nilfold cross R, where this nilfold is a nilfold of degree B. In other words, the Chern number of this nilfold is precisely the degree of these Del Pezzo surfaces. And we can also extend this picture formally to degree 0 by taking this M to be a certain four manifold, which gives rise to, instead of a nilfold, which is a non-trivial two-torus bundle over a circle, just T2 cross S1, or in other words, T3. And in this way, one constructs what's sometimes referred to as an ALH hyperkähler space. And so we end up in this case, with something which is asymptotic to a cylinder given by T3 cross R. So we have a trivial nilfold, which is just a 3 torus here. So now we can resolve all of the singularities here by gluing together Aguri-Waffe spaces of this kind by long neck regions and gluing on Tian-Yau spaces. And the hard part of the mathematics result is, given these individual hyperkähler spaces, they can be glued together to form a smooth, compact hyperkähler space, which is hence a K3 space. And here we see that the Tian-Yau spaces were of degree B minus and B plus. One of each.
Can I just ask you a question?
Yeah.
So is there any relation between these Tian-Yau spaces and Atiyah-Hitchin spaces? Or?
Well, yes and no. I mean, both are given, have asymptotic regions which look like Gibbons-Hawking metrics, but in the Atiyah-Hitchin space, it's asymptotically locally Euclidean. It's an ALE space, whereas here the asymptotic region is something which looks like a nilfold cross a line. So the asymptotics are different, but in principle they're all I guess, resolutions of, they're both resolutions of singular Gibbons-Hawking spaces, which formally look like Gibbons-Hawking spaces with negative mass sources.
So both locally represent Orientifolds somehow, but in different background. Is that the way to think about it?
I mean, locally the metrics away in the asymptotic regions look like Gibbons-Hawking spaces, but and so formally, locally, the metrics look similar, but with different asymptotics, different boundary conditions. So there's some similarities, but also some differences. And
I'm just wondering if one could be some limits of periodic array of the other.
That would be very interesting. But one thing which I don't see from the Atiyah-Hitchin side is the point I was just starting to describe, which is because of the finite classification of the Del Pezzo surfaces, they're given by these degrees which run from 0 to 9. There are corresponding set of Tian-Yau spaces given by a finite set of degrees for the nilfold. So we have this finite classification arising there. So let me say a bit more about the point I'm about to say, and then maybe we can come back to that at the end. But so I think there's a lot of similarities. They're both local geometry is similar, but I think the asymptotics and the classification, which comes from global topology and so on, means that there are some differences. So I don't think I'm not sure there's a one-to-one correspondence. But as we'll see, there's a certain sense in which these Tianyao spaces could be thought of as a basic Tianyao space with some D-branes, or also some Kaluza-Klein monopoles moved onto with some Kaluza-Klein monopole, a limit of moving Kaluza-Klein monopoles onto the Tianyao spaces. So within that picture, it might be interesting to explore to the extent to which that might work out. So based on the fact that the classification of the Del Pezzo surfaces, we get a classification of these Tianyao spaces. There's one at either end, each characterized by a degree, which goes from 1 to 9, and I've extended it to 0 by including T3 cross R as an extension of that. And so this tells us that B minus is the value of the M1 here, B plus is the value of the slope here, and you have a jump at each of the middle points, and the jump is given by the total jump is given by, the total charge has to be 0, so the total of the charges in the middle has to add up to the sum of these two, which is less than or equal to 18. So this almost agrees with the type 1 prime picture where we had similar formulae, but where the charges in the middle had to add up to 16. So it looks as if tantalizingly close to the D-brane picture, but arising in the D8 branes, but now except we get 18 instead of 16. So the type 1 prime, as I mentioned, has got 16 D8 branes and 2 O8 planes. And this is the correct counting for the type 1, for the turbative type 1 theory. But this turns out not to be enough to be able to understand, for example, some of the symmetry enhancements one gets in the heterotic dual, where, for example, one wants to be able to get SU18 gauge symmetry. And so to understand how the SU18 could arise from this picture, I mean, a reminder that if you have coincident D8 branes, you typically get an SUN gauge symmetry on the coincident branes. But it was argued by Morrison and Seiberg some time ago that at strong coupling, the O8 plane can in fact emit one D8 brane to leave an O8 star plane of charge -9. And then if we had these O8 star planes at either end of the interval, then we could have 18 D8 branes on the interval in the middle. And if at tau equals 0, there are n minus branes on top of the O8 star plane, we'd leave something with charge -9 plus n minus. And similarly, we'd have -9 plus n plus at the other end. And now, if we include these O8 star planes, we get precisely the same formula as we got for the degenerate K3. In both cases, we get 18 sources, and in this picture, we can understand, for example, the SU18 gauge symmetry from having coincident D8 branes, 18 coincident D8 branes, or 18 coincident Kaluza-Klein monopoles arising here. So this gives a nice way of understanding how all these different ingredients fit together. And we can look at matching this chain of dualities was at arguing at one point in the moduli space, the orbifold point in the moduli space. And we can ask about extending to other points in the moduli space of the K3. So in the type 1 prime moduli space, it's given by this coset, O117 divided by O17, identified under a discrete subgroup, and an extra factor here, corresponding to the dilaton. And this 17-dimensional space has got this 18-dimensional space corresponds to 16 D8 brane positions, the dilaton, and the length of the interval. So giving 18 parameters. So under this chain of dualities, we can embed the type 1 prime moduli space inside the moduli spaces of the duals, which are strictly bigger, but it will identify a region of the moduli space corresponding to the dual, the type 1 primed. And so if we, for example, look at the this one, the Orientifold of the 2B on T4 mod Z2, we can regard this as being T4 mod Z2. This is identified under the simultaneous reflection in all 4 circles. We can regard this as being T3 cross an interval, where the interval of the ends of the interval, we identify the T3 at the ends to give T3 mod Z2. So it's like a T3 cross an interval, but where the T3s pinch off at the ends. And so we have a long neck where we have this interval corresponding to this interval if the interval is long compared to the length, the size of the T3, but with the ends pinching off. And the moduli comes from the positions of the branes on this interval. And this then clearly maps to the moduli space of the K3 with a long neck, which looks like a nilfold cross an interval, and the moduli coming from the positions of the up to 18 Kaluza-Klein monopoles along that interval. So we see that the duality between the heterotic on type 1 on T4 and the 2A on K3 can be understood as dualities in terms of dualities at the orbifold point when K3 is T4 mod Z2, but they can't be understood as T and S dualities at general points in the moduli space, because T dualities in the conventional sense require there to be isometries, and K3 at general points in the moduli space, where it's a non-singular space, has no isometries. However, the moduli space of the type 1 on T4 and the 2A on K3 are the same, and so the duality at one point in the moduli space could lead to a duality at all points, because one can translate moving in the moduli space of type 1 to moving in the moduli space of 2A. So moving the D8 branes in the type 1 prime picture corresponds to moving the Kaluza-Klein monopoles in the other. And yeah, so I've just said that. This then extends to the non-geometric spaces as well, where so we can move. So for K3, we can move to a region of the moduli space with the long neck, and in the long neck region, it's approximately a nilfold cross an interval. T dualizing will give a T-fold cross an interval, and this can be understood in terms of a double geometry, but I won't say much about that here. But it can be understood in terms of the sources, instead of being Kaluza-Klein monopoles, correspond to these exotic branes, and the arena in which they live is now seen as being this non-geometric background in which they move. This story has got some special holonomy generalizations. How much longer do I have? 2 or 3 minutes. Okay, so one can replace the three-dimensional nilfold with a higher dimensional nil manifold, which can be thought of as a quotient of a nilpotent Lie group by a discrete subgroup, and gives a geometry which is typically a torus bundle over a torus. And it turns out that these spaces give rise to special holonomy metrics instead of hypercalar metrics. And this was based on some old work of Gibbons, Liu, Pope, and Stell. And with my student, we understood that T-dualizing this would replace this special holonomy metrics, which have less supersymmetry, with intersecting Nerva-Schwarz 5 branes, and hence via chains of dualities intersecting D branes and so on. So, so there's a whole range of different cases which give rise to different holonomies, Calabi-Yau manifolds, G2 holonomy, and spin 7. And these special holonomy metrics of Gibbons et al., which were, involved one harmonic function, and dualizing these gave rise to special intersecting five-brane solutions with one function. For intersecting brane solutions, one can generalize this to having a different function for each five-brane, and hence allowing the possible delocalization of this solution. And then dualizing back gave rise to new special holonomy metrics with several functions, generalizing the original one. And then further generalizing this gave rise to new to ones which, instead of being smeared, had so-called semi-local intersections. So in this way, there's a long story which I won't have time to talk about, which talks about an interesting class of special holonomy metrics which arise in a very similar way to the way in which we described the K3 as emerging. So we have a story which is a very rich story about, on the one hand, brane solutions and the other smooth geometries, in which various features of the brane solutions have interesting geometric duals where some aspects which occur at strong coupling in the brane solutions arises at weak coupling in terms of smooth geometry in the duals. So I'm out of time, so let me just conclude. We saw that the nilfold and its duals could be embedded in string theory as giving local solutions by fibering over an interval. So these were torus bundles over a circle with parabolic monodromy. There are lots of other kinds of solutions with other kinds of monodromies which also rise, and there's lots of other stories each of which has got a slightly different work out in a slightly different way. But with the ones we talked about, with the parabolic monodromies, they could be understood in terms of dualizing the type 1 prime theory to give full string theory solutions. So, and we realize the K3 as a nilfold fibered over an interval with Kaluza-Klein monopoles insertions and Tianyao end caps. And this gives a good approximate geometry for the K3, given by gluing together individual incomplete hyperkähler metrics in such a way that you get a complete compact hyperkähler metric on K3. But what's particularly interesting about this is we can very explicitly study the duality transformations of these various ingredients, because at least away from the end caps, we have isometries where we can explicitly do T-dualities. So in this picture, the singularities of the smeared branes are resolved in terms of local sources, local Kaluza-Klein monopole insertions. And the Tianyao spaces gave rise to a geometric dual of the Orientifolds, revealing some of the in particular reveals some of the non-perturbative structure of the Orientifolds. So phenomena which occurred at strong coupling in the type 1 prime picture now arise at weak coupling geometrically in terms of the K3 picture. And it's interesting that there's an intriguing relation to Del Pezzo surfaces, and it would be interesting, and relationships between Del Pezzo surfaces and the kind of duality symmetries of string theory and M theory is a long-standing phenomenon. It's long been realized that there appears to be a magic duality between the story of Del Pezzo surfaces and the classification of U-dualities. And this gives another ingredient to that story which is yet to be understood. And it gives a very nice generalization to all of this story to special holonomy manifolds and intersecting branes, and in particular gives a new way of, an apparently new way of constructing special holonomy manifolds. And what I tried to do is show in this talk is to show how a chain of ideas relating dualities and trying to understand dual forms of those dualities turns out to give some interesting new insights into quite a range of phenomena. So this is part of a lot of some ongoing work, and I think there's still a lot more to be understood, especially regarding these special holonomy manifolds and relationships with intersecting branes and explicit solutions. So thank you for your attention, and I'll stop there.
Any questions? I have one question about these special holonomy manifolds. Are they complete?
So in the K3 story, we started off with this local construction which constructed these Gibbons-Hawking metrics. But then the duality with string solutions, the fact that the type 1 prime is a complete string solution, gave an argument that there ought to be, that following the chain of dualities, we ought to get a consistent background, which indeed we did. We ended up with a compact, complete K3 metric. So with the intersecting branes, I think it's, again, I think the arguments, if you start off with a consistent string background with these intersecting branes, which will, in general, might require some Orientifold planes coming in as well, one ought to be able to end up with a complete compact space. But one of the things is that typically this would include symmetry enhancement. For example, in the case when some of the sources came together. And we know that, for example, in the context of G2 manifolds, from the work of Bobby Acharya and others, that the G2 manifolds relevant for symmetry enhancement always singular. So I think it will lead to complete, the hope is it will lead to complete and compact special holonomy spaces, but possibly singular ones. And one of the questions is whether these are special singular points in a moduli space of a smooth G2 manifold, which would be the hope. But there's a lot more to be understood to make this concrete.
Thanks. Any other questions? In that case, let's thank Chris again.